And Rossen will give a talk on Hamiltonian models for the propagation of irrotational surface gravity waves over a variable bottom.
Okay, thank you. And thanks to the organizers for their kind invitation to the workshop and to the program. This is a joint work with my colleagues Compelli and Martin and Mihail TodorovA, and this is still a work in progress. So in a sense, this is more about the methods rather than the results, and some of the interesting results that are the results with vorticity, they are still in a preparation stage. So here I will be talking mostly about flows without vorticity, although I will mention something at the end. So the Hamiltonian approach has a long history, as it has been mentioned several times. So one of the seminal papers is the Zahar of 1968. And since then there are so many papers that I'm not going to, it's impossible to mention all the names, and the excellent works in the area. So I will only mention papers which are directly relevant to what I'm talking about. So one of the approaches that we will adopt is the Hamiltonian approach based on the works of Craig and co-authors. So this is finite depth and flat bottom for internal waves, and there are papers from as early as early 90s, and there is another one that is for Hamiltonian waves for free surfaces and interfaces. That is a more recent one. In the cases with flat bottom, the Hamiltonian approach, I mean, also vorticity can be piecewise vorticity can be included. So this is a recent work of myself, Adrian Constantin, and Compelli and Martin. And in this Hamiltonian framework, as a rule, allows approximation taking into account different scales. So different approximations lead to different Hamiltonians and ultimately to different models. So as a result, one can derive the various model equations like Korteweg-de Vries, Boussinesq limits, and so on. So the history of works for waves over variable bottom. So some of the pioneering works are by Kakutani apparently and Johnson as early as 1971 and 1973. So they independently arrive at the same equation, which is sort of a KdV with variable coefficients, which is quite an interesting one. And in this talk, I will, as an example, I will adopt this scaling regime from the work of Kakutani and Johnson, and within the Hamiltonian framework of Craig and co-authors. So in this talk, we will see some analysis of the effects that are due to variable bottom. So this is the setup. We have a surface elevation eta. So this is the domain, and we have average bottom, which of minus h, and beta x is a function which measures the deviation from the average bottom. So it's a fixed function, beta x. Okay, so the average of eta is at y equals 0. So the actual depth is at minus h plus this function beta x. So this is the domain of the fluid, and subscript s will be referred to the surface, and subscript b on the bottom, so which is located at this bx. Okay, so the governing equations In the bulk, when we can introduce, of course, potential stream function. This gradient phi can be written also in this divergence form, which will facilitate the divergence theorem later on. We have this Euler's equation in Bernoulli form. We have kinematic conditions on the surface, but also at the bottom. So the kinematic condition on the bottom is this one, because we don't have time dependence. And for simplicity, let's assume that eta, so we consider the solitary case where eta and this function beta and the potentials, they decline fast enough to 0 at plus minus infinity. Okay, the Hamiltonian formulation. So the Hamiltonian, well, this is not yet the Hamiltonian, but evaluating the full energy in the bulk of the fluid can be done by this. So we substitute here the potential and all that, and introducing the potential at the trace of the potential at the surface by this kind of phi. We can actually transform this integral in the following way. So introducing Dirichlet-Neumann operator, which depends on the bottom. So this is the really complicated object that, acting on phi, transforms the normal derivative on the surface up to this factor times the gradient phi on the surface. So all the difficulty of the problem is hidden here in his Dirichlet-Neumann operator. But fortunately, the expansions and everything are known by the works of Craig and Coulters, as we will see later on. And this is, of course, the normal vector to the surface outward. And the Green theorem or divergence theorem can be applied for this term here. Because here we see the bottom, actually, on the bottom, the normal on the bottom is perpendicular to the gradient, because this is exactly the kinematic condition on the bottom. So miraculously, we have only a surface term. So the problem can be, again, related to the problem on the surface. So once again, the difficulty is here in this operator. And the Hamiltonian formulation follows from the variations of these objects. So again, for the variation, we can write in this form. There are variations, again, the Green's theorem on the surface, on the bottom. But again, on the bottom, there is no, as we shall see. And this is the variation from here. We have variation of this term. And we have to be careful that this phi, which is the variations here, they have special relations. On the phi is the potential evaluated on the surface. So if we put all together, we have this expression for a variation of h, which, as I said, dHd, the potential on the bottom is exactly the kinematic condition. It is 0. So h doesn't depend explicitly on phi on the bottom. The variation is also 0. So it's consistent. So in this case, miraculously, the dynamics can be reduced to the dynamics on the surface. So here, the derivative with respect to this psi, which is essentially rho times phi, is due to the kinematic condition is eta t. And the variation with respect to eta is this expression, and with taking into account the kinematic boundary condition and then the Bernoulli's equation, we get that the dH eta is minus psi t. So we have canonical equations of motion, this time again. And with this Hamiltonian, this is the capital B. Of course, this for fixed bottom, this term is not, doesn't produce any variations. It can be neglected from the picture. So, okay, if we further introduce psi x, because psi is actually potential, and psi x is some sort of velocity times rho times constant. In terms of u, the Hamiltonian formulation has this Gothic u, Hamiltonian formulation has this form. Okay, and what is this complicated object? Well, it can be expanded like this. Can be expanded in Gj is contains eta power of j. So eta is the magnitude later on magnitude of epsilon, which is amplitude over h. So this each term is omega eta power of j. And if we introduce also operator minus I ddx, which has Fourier multiplier k 2 pi over 1, the wavelength. So the structure of these terms is like this. The G0 is d hyperbolic tan plus d L beta, and L beta is the the term related to the bottom. So G1 is, all the other terms are recursively obtained by the previous. So the only difference from the flat bottom is this one. And term L beta is really complicated. So again, it can be expanded to the powers of beta, and Lj is beta power of j. So these are recursively, one can work it out, and these are the expansions here up to the first several terms. So this is what this complicated Dirichlet-Neumann operator is. And yeah, so we expand to certain order this operator. So L is well expanded to order eta square is like this. So let's keep the first non-trivial order. So we did the leading order plus this is essentially G1, where L is we have to take into account. We can expand tan, okay, like this, and L1, L2, L3 have this expansion. Okay, so we can reorganize everything like this. So D and D, and inside we have sometimes beta is before D, there is D, and so on. But if we, speaking about the regime adopted by Kakutani and Johnson, if we consider small variations of the bottom, so if we take the function b to depend on this variable epsilon x, where epsilon is of order delta square, because the order of d is 2 pi over lambda is of order delta square in this regime, smaller. So the derivative of beta is proportional to epsilon. So the commutation of beta and d will produce higher order terms. So if we keep the leading order term is okay. If we commute beta and d in the next order, which the difference will be anyhow higher order term inside here, we have this interesting expression that it's h minus beta is the effective depth at the local depth. So this is the local depth cubed, and up to this order of expansion, so the Dirichlet-Neumann operator has this pretty nice structure. So it's B, capital B of capital X is, I should say, the local depth. So I here want to write it because it's kind of important for what follows. So epsilon small x and okay, B so okay, so I don't know, technically it is okay. And this is pretty much it. We can plug it into the machinery and this Dirichlet-Neumann operator, and in the case of slowly varying bottom, and well, introducing all these small parameters as usual, epsilon and delta, that and related to the amplitude of the waves and this average depth and h over lambda, and of course eta is of order epsilon. So this approximation of the Dirichlet-Neumann works up to this order, and d is of course of order delta, because k is of order delta, the corresponding Fourier multiplier and so on. So u equals psi x has the magnitude of velocity and is also of order delta, and we consider this the most famous, I mean the first thing that we should consider is epsilon of order delta square, which hopefully will produce the Boussinesq and ultimately the KdV propagation regimes. Okay, we write now the Hamiltonian in terms of the scaled variables. So actually, so rho and everything is, yeah, so I mean scaling with epsilon and delta. So we have epsilon square and epsilon square here as a common factor. So this is the leading term, and this is delta square because of the dispersion. Eta is order epsilon. So we have these two terms that are of the same order and balance themselves. So there we are with the, in terms of u, we can move the differentiation. See, with this calligraphic u, and we have the Hamiltonian in terms of u and eta. And these are the equations in terms of the so-called Boussinesq regime, in terms of this calligraphic u and eta. So it's a system of equations, but we have to remember that B now depends on the bottom topography. It depends on the Bx. So this is a remarkable system because it generalizes the Boussinesq in the case of variable bottom. Well, of course, in the case when the depth is h, just h, the constant case, this system is even more remarkable because it's an integrable one, and this fact is known but not so well known. For example, yeah, if b equals h, we have this system, and we can remove this term with shifting eta minus h, and then we can make this coefficient 1 over 4 by rescaling of the xt derivatives like this with gamma equals 3 over 4h cubed. So this system is exactly the system, the integrable system that has been discovered by Kalb in 1975. So this is called a Kalb-Boussinesq system, Kalb-Boussinesq equation. It has a Lux-Payne representation. As you can see, theta is here the spectral parameters. This is an isospectral problem, but it's quadratic one because of this. So the spectral problem is this in the class of, although it is scalar function, it's in the class of so-called energy-dependent potentials. So the inverse scattering is not as simple as in the case of KdV. Well, what about the solitons? Well, the solitons, they have been studied by a number of people in number of works. Well, the first time Kalb himself, then other authors. I remember Sattinger, who is not mentioned here, well, including myself, my colleague Tony Lyons, and his later on his student Tony, who is here in the audience. So the solitons of this system, there are interesting solitons. All right, there are left and right running solitons that have been found by Tony, but there are also topologic kind of solitons that are oscillating at near one point. I mean, we can I call them topological because we can fix them to the origin, and they kind of oscillate around the origin. Some people, they can equally well call them breeders. So I'd say not all of these solitons are relevant to the water wave systems. But I mean, there are left and right running solitons, and this is something that that one can expect. for a disturbance to create left and right running waves. Okay, so going back to our system with variable bottom, the leading order terms are here, and we can exclude one of the variables, and we can write for eta the elevation like this. And we see that this is kind of a wave equation with velocity that depends on this term, slightly varying velocity. So now, approximately square root of g times the local depth. Okay, so this is not a big surprise. So this just means that in the leading order, what happens if we have some initial condition, it propagates with this velocity that is slightly changing due to the uneven bottom. Okay, and in the leading order, this Gothic U is like this. Okay, but this also suggests that the variable x minus this cxt is an interesting variable. It's like the new characteristics that should be considered. So this indicates that the proper variables necessitate something like x minus ct, that following the work of Johnson, we can look for a slow variable of this form, some function of capital X over epsilon minus t, which is reminiscent of the far-field variable x minus t. What is R? We can decide later on. We can discover this as a next step when we plug it into the equations and when we can see what's going on. We can change the derivatives like this. The operator d now has this form. This is the derivative of R. Well, there the dx derivative has coefficient epsilon, and the leading order equations are like this. And they, if we multiply eta u theta, eta theta. So the only way to make them compatible is to find that Rx squared g times b equals 1, or R prime is plus minus. So let's take, well, apparently related to the left-right running velocity, let's take the positive sign. So it is 1 over the local velocity, R prime. So formally, we can say that R is integral of this, and the characteristic at point x near x1, which corresponds to x1 over epsilon, can be evaluated like this. We expand a bit around x1. This is R prime. This is 1 over c over x1, and the rest is just a constant. So the characteristic is x over this minus t. So in other words, this theta still measures the space dimension, but in a co-moving system, in an observer who moves with the main wave, in a sense. And then we can write the equation in the new variables up to this order, which is not so difficult. And well, you see u theta can be plugged in here and excluded because we know how to relate these things. And u in leading order is related to eta, so we arrived at this equation. So we have epsilon delta square. So epsilon and delta square terms, they balance across themselves. So c is x dependent, but on the slow variable x. So we can put it into even more compact form, introducing square root c times eta. So then it really looks like a KdV with coefficients depending on capital X. So this, I call this Johnson-Kakutani equation, or JK equation. So now we see that theta is the space-like variable. So this is the distance as measured from the co-moving observer. And here it seems though that X plays the role of time, right? So this is a bit unexpected feature for the equation, but it's not so unexpected because when we speak about the for example x minus t, these far field variables, approximately both x and t are order, this small x small t are order 1 over epsilon, and this is order 1. So up to the leading order, both small x and small t can measure x, but they can also measure time. So in this case, we have in this case we have basically time-dependent KdV. KdV with variable coefficients. And well, if of course the dispersion is really small compared to epsilon, we have this Burger's equation, which regardless on what the dependence is, does not support globally smooth solutions anyhow. Okay, so this model has been studied previously in the works of Johnson, Knickerbocker, Kalb, and Newell. So this model is also interesting because the change of variables, so basically in these works, they have noticed that one can change the variables and bring it into KdV form plus perturbation. So this can be done, can be considered also as perturbed KdV, where this perturbation depends on this. Well, but for the analysis or perturbation of KdV, there is a general theory which is complicated enough and actually doesn't give very neat results. So I'm not going to go to this direction, although that this can be done. So rather, I would continue with, again, following the work of the ideas in the work of Johnson from analyzing this equation, where it's essentially time-dependent KdV. So the good news. So the bad news is that some of these time-dependent KdVs are classified, and it's known which one can be transformed to the KdV with constant coefficient. This cannot be done in this case. But nevertheless, there is something that we can say about this equation. So now I'm going to replace x with tau, because I explained that x measures x direction, but it's also in the leading order measures, it's like a measure slow time. So the co-moving distance is theta, and slow time is measured by tau, which is the same as capital X in the context of this specific time-dependent KdV. And if we take g, let's take g equals 1 for simplicity, the other constants, and this is the bottom variable. And let's specify this b with this profile. This corresponds actually to a bottom of this font, like so I can do it here. So this is so this hyperbolic tan, and this is x, which also corresponds to slow time tau equals 0, which is the same. And yeah, we decided to, with my colleagues, to see how, to investigate a bit numerically the result suggested by Johnson. The idea is that here and in this part we have basically constant depth b0, and in this we have constant depth b, and here the depth is changing. So here we have KdV is effectively with constant coefficients, and if we start with an exact one soliton solution, this soliton moves with time to here, where it sees the obstacle that is switched on at t equals 0. There is an obstacle, and something will happen to this soliton. So yeah, but transforming to the canonical form KdV with this minus, so we take as an initial condition this Sech soliton coming from tau equals, say, minus infinity. So it's transformed to the canonical KdV, so it's minus Sech squared. And tau equals 0, the equation changes because the coefficient changed from B0 to B. So it's not anymore for the new B. This is not one soliton solution. So this is an initial condition for the new equation of this form where K is constant. So by the way, this coefficient 9/4 appears in Johnson, but the work of Johnson, but also he mentions another earlier work of Tappert and Zabusky. So apparently this has been studied a lot in these years, and it's amazing how, because this is actually a tricky question, and back in 1971, 2, 3, these are the infancy years of the soliton theory. So people didn't know that much about solitons. Anyway, so this is kind of a problem that is also related to quantum mechanics. We have some coefficient. Well, without this coefficient, the initial condition would give us a soliton, but in general not. So it's a potential, like we can, let me remind you that KdV has, well, the one soliton is this. So we have the one soliton solution is of this form. We study now the effect of this constant that appears in the initial condition. Okay, and the KdV has this Wax pair representation. Here is the spectral problem. So it's like a spectral problem in quantum mechanics with minus h square potential. So this has been, problems like this have been known for a long time in quantum mechanics. When you have minus h square potential, so this is the, say, theta spectrum, and this is, say, theta, okay, our, so we have number of negative discrete eigenvalues, and we have here spectrum, the continuous spectrum. Okay, and so the problem can be transformed with change of coordinates and so on to the Legendre equation in this form. Z is the new variable, that is tan k times theta, and here we get the eigenfunctions are of this form, with the L2 functions that are the only sensible solutions for the Schrodinger's equation, time-dependent Schrodinger equation are these. Well, these are the discrete eigenvalues, and the constant B, which remember is this one, has to be 2 times, which should be nn plus 1, the quantization condition. So we have a set of eigendepths which are related to the number of the solitons that can be, that would appear here under the, when the obstacle is met. So, as I said, this has, okay, let me see. This result appears in Tappert and Zabusky. As I said, Physref letters also discord. I read their paper, but I couldn't actually understand exactly what is in there. But anyhow, so this is how n should depend on alpha. Alpha measures this threshold. Well, but there are idealizations because we are in the reality of the slowly varying bottom. So this thing is for a jump here, and we don't want a jump because we have to some sort of regularity here has to be assumed. Okay, and this is it. We can test here the number, how many solitons, and what happens actually. And we studied this numerically to put to the test this theory, so to say. And there we are. Well, it says that theoretically the first splitting of the one soliton will appear at alpha equals 0.24. And here what we see is that alpha equals around 0.3. So this is actually the time. Yeah. So we start from a, let's say, the one soliton solution with the time. This is theta, the space dimension. So here already it starts to form, and if you see closely, we'll see that there is a small one And this is the main one that is losing some of its energy. This is apparently a small eigenvalue, and therefore small amplitude, so small velocity. So it's quite a slow one. And if we go further to increase to 0.5, we see that the second one is already quite visible. So one soliton, and the threshold it splits into two. And then we increase the amplitude from 1 to 3, so it's a big one. But the results, they should not depend on the amplitude, right? We still have 2, but this energy is dissipated slightly in these waves of radiation that are forming, and they are kind of reflected here from the from the obstacle.
So they're moving backwards?
Yeah, it seems that they're moving backwards. They're reflected. So the solitons are moving forward. So the one soliton gives birth to 2 solitons. And in the solitary case, we decided to see what happens if we have the opposite situation. I mean, shallow to deep. Well, in this case, we should not have solitons, and this is what happens. So we have still one soliton moving further, and waves of radiation, so it dissipates radiation. Actually, in the work of Johnson, the periodic case is completely different there. So here I don't speak about the periodic case. So in the periodic case, there are new solitons even for when you go from shallow to deep. Okay, and finally there we are. Here we have alpha is quite big, 0.8 in the case of big threshold. So we have several, 1, 2, 3, 4, 5, even 6, something like 6 solitons are forming when we have this bigger threshold. And well, of course, these results of the eigendepths, they are not fully confirmed, but I think that there is a reason for this, and the reason is, as I said, that there are several assumptions. First of all, this is a smooth threshold, plus there are also here other effects. I mean, waves of radiation on the continuous spectrum, and so on. Okay, so we finally several remarks. What I can say is, yeah, we have started from Hamiltonian variables, and apparently the fluid motion in the entire domain can be recovered in principle from the boundary, which includes surface and the bottom. Well, actually, in this work that I've been using most of the time of Craig and Coulter's, they provide a formal expression which relates, where you can extend the potential from the surface into the whole volume. So apparently, in this case, it's we can extend the problem from the surface to the volume of the fluid as well. And okay, so there are, of course, many other possibilities for. They are considered in other papers like random topography, etc. And currently, as I said, we work on the incorporation of vorticity and effects like this in variable bottom. This is another very interesting problem. And in this case, probably the influence of the bottom, the potential of the bottom, will not be possible to be eliminated like in the case of the irrotational case. So it's in a sense a higher, even in the case of constant vorticity. Well, of course, there is also the several layers, internal waves, and more layers. And Okay, so this is pretty much it. Thanks to the organizers of this interesting workshop. And special thanks to Professor Adrian Constantin, Professor Robin Johnson, Professor Matsuno for many valuable discussions during the program. Okay, thank you.
Very much. Questions? Remarks?
Yeah.
So you have an epsilon for the bottom, and it's the same epsilon. I mean, in the beginning you had an the variation of the bottom was epsilon, and then you have another. It's the same epsilon.
Yeah, actually for the bottom I didn't introduce anything. I just limited the expression to the third order term. So, but you're right. We something should be. And the third order expansion actually because it matches the result that I knew that it's about to follow. But yeah, so it's a good remark.
I can give a response to that if I may. When I first started the problem, I had the small parameters associated with KdV, evolution, etc. And then the problem was, that I posed for myself was, what problem do I then do with variable depth? And clearly you could do a depth that varies on a scale, which is either faster or slower than the KdV, both of which can be done quite easily, and it's not very interesting. The most interesting was when the two scales were the same. That gives rise to all this structure. So, yes, they are the same, and that was the reason why.
One question. What am I thinking wrong? I'm thinking in the case that case of the Tench ramp, right? You have a constant depth here, a constant depth there.
Yeah.
So what am I thinking wrong is that the KdV is a unidirectional model, and here you were seeing some reflections. So what am I'm a little puzzled. Maybe I'm missing something.
These were waves of. Basically, the solution is.
Radiation. So are you in a moving frame? I got a little confused.
Yeah, it's
with
in a
reflection with the
co-moving.
unidirectional model. Or
Well, this is co-moving frame, but I mean the nature of the solutions, they are in the whole space. I would not be surprised that the waves of radiation propagate backwards because in general the solution, the soliton solution is like this. And the structure of the full solution is like this. So I should write what eta x theta in my case. Basically, there are some x. Okay, let's say tau. These are the scattering data from probably 0 to infinity. This is tau theta, and this is sine. This is theta. This is the eigenfunction square d lambda plus. These are the soliton solutions. So d lambda is from they would be decaying. Oh, I have to think, but basically this radiation part comes from the whole spectrum. So
I'm missing something. I'm still puzzled.
so
In the numerics, right?
I would
in the numerics, you're solving KdV, right?
yes,
And with those red lines and so on.
yeah. But I would, I don't know if. Frankly, I'm not an expert on these waves of radiation and long time behavior, but I'm not so surprised that they are going backwards because they somehow have contribution from all parts of the spectrum. Solitons, they have one, they're related to single discrete eigenvalue and have specific velocity. But I mean, this, of course, probably is something that we have to think how to how to explain. Well, this is just something that comes from numerics, but Yeah.
Other questions? Thank you again, Ross.
Okay.